If you remember, a few days ago, we talked about some compound interest formulas. They are exponential in nature because of the time usually is the variable, and the time is in the exponent. So this is an application. The compound interest formula is an application of exponential. Recall with me then the formula for the compound interest. We had two of them. We had A equals P parentheses 1 plus R over N raised to the NT power. That was one of them. And the other one was a little simpler. Looks like A equals PERT, is the way I remember it. P e to the RT. Those were the two compound formulas we talked about. And remember the distinction between when did I use, well, I guess easy way to remember. This one I use in one certain case, and that is when what? Compound continues. Yeah, if I'm compounding continuously, that's the formula to use. If I'm compounding any other way, semi-annually, quarterly, monthly, yearly, daily, this is the one. That's the formula to use for that. Okay, so with that in mind, let's look at number one on the handout here. So I've got 5,000 invested at a rate of 7.15% compounded quarterly. How long will it take to invest the investment to grow to 7,500? So basically I'm looking for the time to grow to 7,500. All right. So in this case, thinking about those two formulas, compounding, and what we just said, this is compounding quarterly, so it is the more complicated one looking. That's this one. So I'm using this formula since I'm compounding quarterly. All right. Now, which pieces do I have here? What is the 5,000 in this formula?
P.
That's P. Yeah, that's what I start with. P is the principal, the amount you start with. Of course, that's the R. Now, of course, to plug it in the formula, we're going to change that over to, without the percent sign, even though it's got a decimal, it's still got the percent there, and so I need to change that and move that decimal place 2 places back, so it's 0.0715 that I'll use for R. Now, compound quarterly, what does that mean to the formula? That's the N value, and N is the number of times compounded in a year. So if it's compounded quarterly, that's 4 times per year. So that would mean N equals 4. What about the 7,500? That's the A, yeah. That's the amount I want to end up with. And so that in this formula is A. So let's plug those in. We got 7,500 is A. The P is 5,000. 1 plus R, like I said, change the R to 0.0715. The N is 4. And then 4. And then T is our variable, right? That's our unknown here. So I'm trying to find the T. Well, initially, simplifying that out, really all I can do is I can combine the numbers in here, 1 plus that divided by 4. That'll be something I can simplify. That in here is 1.017875. That's not. What I recommend is, yeah, that's a long decimal, but I wouldn't yet round off, because if you round that off to 1.02, you'll be way off. Okay, so don't round right here. Don't round yet. Okay, because if you round there, it'll throw your numbers way off. All right. Well, so looking at this problem, what I've got here is it's an exponential equation. I got to solve for t. T is in the exponent. That's an exponential equation. And the technique, when you don't have the same base on both sides, the technique is what? Remember what we do on exponentials? LN both sides. I want to LN both sides. Now, before I can LN both sides though, I've got to get that by itself. In other words, get rid of the 5,000. It's times that exponential expression. So divide it. So I'm going to start here by dividing by 5,000. Start this off. And 7,500 divided by 5,000 is 1.5. Yeah. So I get 1.5 equals that exponential. Like I said, now we can take the ln of both sides. Because when this is a logarithm, I can move that power out. I can't do it, I can't just move it out automatically. But if it's a logarithm, I can move that power out. So that's why we do the logarithm thing. Because I can bring that power out in front here. And so I have ln of 1.5 equals 4t times the ln 1.017875. Power in front. All right. Well, now I can solve for t because, I mean, it's not nice numbers, but or this one's not nice, but it's just two numbers multiplied by t. So how do I get rid of it? I divide them. So divide both sides by 4 ln 1.01. So it's a little more to write, but you don't want to round it off until you get kind of at the end. And so again, be sure when you put that in, that'll be your t. Whatever that is, that's what t equals there. All right, so ln of 1.5 divided by parentheses 4 ln 1.017875. I get 5.72. That would be a good approximation there. And then remember, for this formula, time is in years. Yeah, the formula overall, the time is in years. So it's 5 3/4 years. All right, is that okay? Questions? Number 2, 2,000 is in an account that earns 4.5 interest. So the rate is 4.5%, compounding continuously. How long will it take the investment to double? Time to double. Well, in this one, we've got compounding continuously. And so like we just said, if it's compounding continuously, it's the PERT formula, right? A equals P e to the RT. The amount I start with is P, so that's the 2,000. E, the R is 4.5%, but again, that needs to be 2 places back, 0.045 is what I would plug in for the rate. T is the unknown. And in this case, we also know the A, the future amount, because I want the original amount to double. And so what is A?
4,000.
That'd be 4,000, yeah. So this is the equation to solve. A little nicer looking one than this, but it's basically the same idea, isn't it? It's an exponential equation. You got to get the t out of the exponent there, so exponent. I want to ln both sides, but ln both sides, I need that by itself. So what's the first step here? Divide by 2,000. So that's 2 equals e to the 0.045t. Now I can ln both sides, so ln2 equals ln e to the 0.045t. That t pops, exponent pops out, so it's 0.045t times ln of e.
And then what would
And
be canceled?
this is a better equation in a lot of ways because ln of e is 1. So it's just ln of 2 equals 0.045t. And so to get t, all I have to do is divide by the 0.045. ln of 2 divided by 0.045 should be about 15.4 years.
What did you use?
Okay? Question?
I'm not gonna do that right the last Thursday.
Is that okay? Look right? Do we agree? Okay with that? Okay. Well, similar problems come up in some other situations. Exponential growth or decay. Is another model that's very similar. And this is one way you can see it shown. Y equals y0 e to the kt, which, if you think about it or look at it, that's a whole lot like the compounding continuously formula. It's basically the same thing. But we're calling it exponential growth or decay of quantities such as population, radioactive material. Yeah, so notice the similarities between that and compounding continuously formula. The y here is the future amount. The y0, well, that's the amount you start with, the initial amount. Why is it called y0? Well, that's because that's at time 0, basically what that means. The initial amount is y0. So this y0 is what we're talking about there. It's just the initial amount. It's the amount you start with, like the p over there. It's the amount we start with in the account. K, well, that's the rate of growth or decay. Now, it could be a growth or it could be a decay. Now, how do you know which is which? Well, if it's positive, if you have a positive k, it's growth. Decay if it's negative. So if k is positive, it's growth. If k is negative, it's decay. Because of the increasing and decreasing, we talked about that with the graphs. If the exponent's positive, that's increasing, so it's growth. If the exponent's negative, it's decaying. It's decreasing. Remember about our graphs there. Okay. And t is the time. Of course. Okay. And in this case, t could be anything. Months, years, it just depends on what. Minutes. All right, and I already talked about why is it growth if it's k positive? Well, that's because it's an increasing function. If k is negative, then it's decreasing, so it's decay. All right, so let's look at a couple of problems here. So we got population of Smallville, this is number 3. Y equals 50 e to the 0.27t. T is the years after 2000. So what's the initial population in the year 2000? Well, a couple ways you could get that. The initial population is times 0. So if I plug in t to be 0, that would be e to the 0, which is 1, times 50. It's just 50. So that'd be 50, there's no units on it, so it's just 50. Okay. The initial population is 50. What's the growth rate? 0.27, yeah. 0.27, 27%. So that's just getting you to understand that this is the initial population, this is the growth rate, or decay rate. In what year, according to this model, will the population reach 5,000? Well, if it tells me the population is 5,000, where does that go?
The Y.
That's the Y, yeah. So that's A, B. Population is 5,000. When is the population 5,000? Well, that's the Y, yeah. And so, again, there's our same old equation there. Divide by 50. So that's 100 equals e to the 0.27t. Ln both sides, so ln of 100 is ln of e to the 0.27t. That brings down the power there. 0.27t times the ln of e. Well, ln of e is 1, so all I have to do is divide by 0.27, isn't it? Done this one a couple of times now, so. So that's 17.056. So that's 17 years. And it years started in 2000, so that'd be 2017. Okay. All right, so we got A equals A0 e to the negative 0.231t. This is an exponential decay model because you got a negative exponent. Okay, so it's decay because it's a negative exponent. If 600 grams of plutonium is observed, find the amount after 21 years.
25.
So the time is 25. Yeah, so that, where does that 600 go? That's the initial amount. So that's A0, right? So you do 600 e to the negative 0.231 times t, which is 25. So whatever that works out to be. .86, is that right? So there's not much of it left. Okay, B, oh yeah, half-life. So what is the half-life? Well, if you've got a decaying model, the half-life is just the time it takes for you to have half of the amount left. So a half-life is a time. The time is unknown here. That's what I'm trying to figure out. Well, if I use the 600, what I'm trying to figure out here is the t, the time it takes to half that amount. So what's my future amount? If I want to know when, it'd be 300, yeah. You know, the previous problem we had, what's the time to double? Well, this is the time to half, okay? That's what half-life means. It's the time to have half of the amount. So if I start with 600, I want 300 to be the future amount. With me? So yeah, so then we divide by 600. 300 divided by 600, of course, is 0.5. Ln both sides. power comes out. Negative 0.231 t. The ln of E is 1. So all I have to do here is divide by negative 0.231. Several examples of this. All right. So ln of 0.5 divided by negative 0.231. 3 years. Good? All right, got one more. No, we done.
So on that last one,
Question.
I got 2.16 as the number, so was it to get,
Mine came out to be 3. ln of 0.5 divided by negative
oh, I
0.231.
didn't have the ln, that's
Okay.
where I forgot.
Okay. All right, number 5. We've got the shoulder height h of an elk is 116 log x plus 40 minus 176. Nice little model, but it's a logarithmic model. Example here. Other examples, like I said, are earthquake magnitudes and things like that. But this is the shoulder height of an elk with antler spread x. Both of those are in inches. So find the shoulder height of an male elk with antler spread 90 inches. Well, that gives me the x, doesn't it? That's the x value. So the shoulder height would be 116 log of 90 plus 40 minus 176. So that's just plugging in numbers. Just going to evaluate 116 log of 130 minus 176. So if you punch it in your calculator, you got it. 116 times the log. Now this is LOGE, log base 10. Get a different answer if you use ln. 130 minus 176, 69.2 inches. So that was just plugging in. B, though, a little different story. Find if the shoulder height is 78 inches, what's the antler spread? Well, in this case, what are we given? That's the h. So we've got the h is 78. I have to solve for x. How do I do that? Well, it's a log equation. And basic idea is I need to get the log by itself. So I've got to do a couple of things before I can do my solving here. Add the 176. I've got to get rid of the 176 and the 116. So I add the 176, 78 plus 176, 254. Then got to get rid of that 116, so divide the 116. Now to get rid of the numbers around the log there.
2.189.
And again, I wouldn't round off too much here.
89655.
Yeah, I'd probably go at least 5, yeah. Let's go 5.5. If you have to round, don't round off too much. Now, what's the last step here? What's next to last step, I guess, but what do we do here? How do we solve it? Got log base 10, so I need to exponentiate both sides to base 10. So 10 to the 2.189655, thereabouts, equals 10 to the log of x plus 40. That'll cancel out that 10 and that log. that log power. This is, so 10 raised to the 2.189655. That's 154.75. 674 equals x plus 40, because that cancels out. Let's just subtract 40, isn't it? That'd be 114.75. No, I hurried on that, but any questions on that? That's inches.